So here we have a random matrix 8, 5, 3, 2, and on the right hand I have my expression for calculating the inverse of a matrix. So we can immediately write R1 as 8e1 plus 5e2 coming from this line here, and from this column here we write R2, which equals 3e1 plus 2e2, and now we can make their wedge product, R1 wedge R2, which will be 8 times 2, this is 16e12 plus 15e21, which equals e12, because we are swapping this sign, which is minus e12. Okay, fine with me. And now we get R1, R2 minus 1, which, remember the expression that we got before, where the inverse of it will be 1, in this case, divided by R1, R2 square, R1, R2. And if we calculate the square of it, that's very simple, because the square is minus 1, and we have here 1 minus 1 times e12, so this is minus e12, and this is very easy to verify that R wedge R2, R1 wedge R2 minus 1, this is equals to e12 times minus e12, which equals e12 e21, because we can swap the order of this. Remember that this notation is only valid when we are dealing with orthonormal frames. Okay, that's very important. And here we can group it, and we call it, and this is obviously 1. Okay, because this is equal to e1, e1, e2, e2, e1, so this is a 1, and the remaining other two objects is another 1, so this is equal to 1, and this is the inverse that we needed. Nice. And now we can obtain directly b as minus e12 multiplying. I'm gonna apply directly the expression that I have up here. So e1 wedge R2, so I come here to the left of the screen, e1 times R2, this is 2 e12, e2 wedge R2, so this will make survive only this one and make 3 e12. I'm forgetting I have 3 here, minus 3. Now we get R1 wedge e1, which kills the first term and survives the second one with the reverse sign, so minus 5 e12. And now we look at R1 wedge e2 on the right. So we got on the right, this is 8 e12. And if we multiply now e12 times e12, considering that the square is to minus 1, this gives us a minus, with a minus that is a plus. This is a minus plus, this is minus 3, minus plus, and this is minus 5, and this is 8. And this is, and you can check by yourself with usual inverse algebra techniques, the inverse of the matrix A. And here I want to show you this Wikipedia quote that says, when a linear system solution is introduced via the wedge product, and here I add a quote because you don't need only the wedge product, you need the geometric product, otherwise you cannot define the inverse of a multivector, as we did before. Cramer's rule follows. As a side effect, and there is no need to lead up to the end results with definition of minors, matrices, matrix invertibility, adjoints, cofactor, Laplace expansion, theorems of determinants, multiplications, and row-column exchanges, and so forth. So basically, with this technique that we have developed, which looks very natural and very geometric, we are dispensing with a lot of the other necessary techniques that we had to introduce in linear algebra to calculate the inverse. Remember that the Cramer rule has the inverse of the determinant, and from the inverse of the determinant we have to calculate the matrix of cofactors with the alternating sign that is a little bit out of the blue. You calculate it and you say, okay, why there is an alternating sign? But here it all appears very naturally with the anti-commutativity of the wedge product. Moreover, if we look to our definition of the matrix inverse, which is this one here, we can compare it with the standard expression for the inverse of a matrix, A minus 1, which is 1 divided by the determinant of A. And this is the matrix of adjoint of the cofactors transpose. And we can identify this term with this term. And we then see that indeed the determinant of a matrix, if we consider the matrix as an operator that acts on a vector and produces other vector, as we saw in the part in module 2 for linear algebra, the determinant of the matrix is how the volume, which is the volume of the transformation in the sense of if you apply the matrix to a unit volume, or in this case area, for example, to let's make a picture of this. So if you have in a two-dimensional space let's make a space here on the right. If we have an orthonormal basis E1, E2, and now you apply a matrix A to E1, and this gives you a vector A, and apply the matrix A to E2, and this gives you a vector B, which in general will be different to what you had before. So this object here had area 1, but this object here, which area does it has? Well, the area of this new object is the determinant of the matrix A. That is exactly the case. And when we go to higher, this is not new, but it's nice to see the identification here. And when we go to higher dimension problems, then the area becomes a volume in 3 dimensions, and we will have the wedge product of 3 vectors. 4 dimensions, then we have an hypervolume, and so on and so forth. So here we immediately identify the determinant of the transformation with the area, in this case, because we are working in 2 dimensions, but with the outer product of the objects that gets transformed by the matrix.